Today, we will look at some problems about the hydraulic efficiency of open channel sections and energy principles in open channel flow. So for the first problem, we need to derive the relationship between the depth of flow and the width for a rectangular channel that is most hydraulically efficient, and use example 6.4 as a guide and show all steps. So based on the example 6.4, the water cross-sectional area and the weighted parameter of rectangular sections are A equals B times Y, and the P, the weighted parameter, equals B plus 2 times Y. And substituting for B, we can get that the P equals A over Y plus 2Y. And according to the Manning's equation, to maximize the Q for a given area, we need to minimize the P. So that's the first derivative of the P respect to the Y equals 0 to obtain the minimum value of P. So dP over the dy equals minus A over the y squared plus 2 equals 0. And we can get that the A over y squared equals 2. And we know the A equals by. So we can get that the B equals 2y. So this is a relationship between the depth of flow and the width for a rectangular channel. So we have done this problem. For the second problem, a concrete open channel is required to pass a flow rate of 42.5 cubic meter per second, and we need to design the best hydraulic trapezoidal section for the channel. I found that we can solve this problem since one condition is missing. So I added the condition here. We assume that the slope of this channel is 0.01. So now we can solve this problem. And based on example 6.4 in the textbook, we know that the best hydraulic trapezoidal section is a half hexagon. And we know that the M equals square root of 3 over 3 equals cotangent 60 degree, and it equals the 0.577. And we also know the B equals 2 times square root of 3 over 3 times y. So the B equals 1.15 times y. And then we will use the table 6.1 in the textbook, and we know the area of the trapezoidal section A equals B plus M times Y, and we know the B equals 1.15 times Y, and M equals 0.577. So we can get that the A equals 1.73 times y squared. And the P equals the B plus 2 times y times square root of 1 plus m squared. And the B equals 1.15 times y, and equals 0.577. So we can get that the P equals 3.46 times y. And now we will apply the Manning's equation. We know the Q equals 1 over N times A times RH to the power of 2 over 3 times SE to the power of 1 over 2. And we also know that RH equals A over P. So we can get that the Q equals 1 over N times a to the power of 5 over 3 times p to the power of negative 2 over 3 times se to the power of 1 over 2. And we rearrange this equation, and we get that the q times n divided by the se to the power of 1 over 2 equals a to the power of 5 over 3 times p to the power of negative 2 over 3. And from the problem, we know the q equals 42.5 cubic meters per second, and the SE we assume that is 0.01, and we also know this is a concrete open channel, so from the table 6.1 in the textbook, we know that the n equals 0.013. This is from the table 6.2 in the textbook. And we also know the a equals 1.73 times y squared we calculated before, and the p equals 3.46 times y. So we can get that 5.07 equals y to the power of 8 over 3. So we can get that the y equals 1.84 meters. And according to this equation, so we can get that the b equals 2.12 meters. So we have done this problem. For the third problem, we need to use two methods to compute the flow classification for the 3-meter wide rectangular irrigation channel. The Q equals 25.3 cubic meters per second. The YN, the depth of flow, equals 1.2 meters. So for the first method, we need to compute the flow number, and we know flow number equals V divided by the square root of G times D. D is a hydraulic depth. Since this is a rectangular channel, so the D is equal to the depth of flow. So the D equals YN equals 1.2 meters. And we know the velocity V equals Q over the A, so equals Q divided by the B times YN, since this is a rectangular channel. So, and we know the Q equals 25.3 cubic meters per second, and the B equals 3 meters, and YN equals 1.2 meters. So we can determine the V equals 7.03 meters per second. And then we can determine the flow number, F equals 2.05, and this value is greater than 1, so the flow is super critical flow. For the second method, we need to compute critical depth first, and then compare it with the depth of flow. And we know the critical depth y sub c equals the cube root of q squared divided by the g times b squared. And we know the q equals 25.3 cubic meters per second, and a b equals 3 meters. So we can determine the y sub c equals 1.94 meters. Since 1.2 meters is less than 1.94 meters, so the flow is super critical flow. So we have done this problem. For the first problem, a flow of 834 cubic feet per second is conveyed in a 10 feet wide rectangular channel at a depth of 6 feet. And what is the specific energy of the channel? Is this flow subcritical or supercritical? If n equals 0.014, watt channel slope must be provided to produce a uniform flow at these depths. So to determine the specific energy of the channel, we know the specific energy E equals Y plus the V square over the 2G. And from the problem, we know the Y equals 6 feet. And we know the V equals Q over the A. Since this is a rectangular channel, so also equals Q divided by the B times Y. And from the problem, we know the Q equals 834 cubic feet per second, and the B equals 10 feet. So we can determine the velocity equals 13.9 feet per second, and then we can determine the specific energy of this channel E equals 9 feet. And then we use flow number to determine the flow classification. And we know the flow number NF equals V divided by the square root of G times the D. And we know the V equals 13.9 feet per second. We calculated before. And I think this is a rectangular channel, so the hydraulic depth D equals the depth of the flow, so equals Y equals 6 feet. So we can determine the flow number. F equals 1. So this is critical flow. And to determine the channel slope, we need to apply Manning's equation. And we know the Q equals 1.49 over N times A times RH to the power of 2 over 3 times S to the power 1 over 2. And we know the Q equals 834 cubic feet per second. And we know the N equals 0.014. And the A equals B times Y, so equals 10 feet times 6 feet. So the cross area is 16 feet square, and the P, the weighted parameter, equals B plus 2Y, so equals 6 feet plus the 2 times, or 10 feet plus 2 times 6 feet. So the value is 22 feet. And we know the RH is a hydraulic radius equals A over the P. So the value is the 16 feet square over the 22 feet. And now we can determine the slope as equals 0.00448. So we have done this problem. For the last problem, a hydraulic transition 100 feet long is used to connect two rectangular channels 12 feet and 6 feet wide respectively. And the design discharge is 500 cubic feet per second, and N equals 0.013. And the slopes of the channels are 0.0009 for both. We need to determine the change in the bottom elevation and the water surface profile in the transition. If the energy loss in the transition is 1.5 feet, and is uniformly distributed throughout the transition ends and shown the uniform depth before and after the transition. So for this for this problem, first we need to determine the water depth at transition entries and exit. So we apply Manning's equation at the entries and we know the Q equals 1.49 over n times a to the power of 5 over 3 times p to the power of negative 2 over 3 times se to the power of 1 over 2. And we know this is rectangular channel, so the A equals bi times yi. The I means the inlet. So we know the width of the entries is 12 feet. So A equals 12 times yi. And we also know the P equals bi plus 2yi. So equals 12 plus 2 times yi. And we know the n equals 0.013. The SE equals 0.0009. And the Q equals 500 cubic feet per second. So we can determine the yi is approximately equal to 5.88 feet. And now we can determine the velocity at the entries. So Vi equals Q over the A, and we know the A equals Bi times Yi. So equals 500 cubic feet per second divided by the 12 feet times 5.88 feet. So the velocity equals 0.09 feet per second. We also can apply the Manning's equation at the exit. Q equals 1.49 over n times a to the power of 5 over 3 times p to the power of negative 2 over 3 times se to the power of 1 over 2. And the A equals BE times YE. The E means the exit. So it equals 6 times YE. And the P equals the BE plus 2YE equals 6 plus 2 times YE. And we know N equals 0.013. And the SE equals 0.0009, and the Q equals 500 cubic feet per second. So we can determine the YE is approximately equal to the 13.4 feet. So we also can determine the velocity at the exit equals Q divided by the BE times YE equals 500 cubic feet per second divided by the 6 feet times 13.4 feet. So the velocity at the entries equals 6.22 feet per second. And then based on the energy balance, we know the HI equals HE plus the head loss. So Vi squared over the 2G plus Yi plus Zi equals V squared over the 2G plus Ye plus Ce and plus the head loss. And note that netting ZE equals 0. And we know the VI equals 7.09 feet per second we determined before, and the YI equals 5.88 feet, and the VE equals 6.22 feet per second, and the YE equals 13.4 feet. So now we can determine that the ZI equals 8.84 feet. 8.84 feet. So this is the channel bottom height at the inlet. Now we can draw a side view and a top view of the transition. This is a side view, and we know the water depth at the entries is 5.88 feet we calculated before, and the ZR equals 8.84 feet we also calculated before, and the water depth at the exit is 13.4 feet. And we know from the problem the length of the transition is 100 feet, and the energy loss in the transition is 1.5 feet. And this is the top view, and from problem we know the width of the entries is 12 feet, and the width of the exit is 6 feet. And since the transition is used to connect two rectangular channels with different widths, so the widths of transition are different at the different section. So on the dashed blue line indicate that we will determine the water surface elevation at these sections later. And then we can create a table to show the change in the bottom elevation and the water surface depth. So the head for the table is the other section, and the width B, and the Z H E Y. In this section, we will determine the water surface elevation at these sections inlet. 25 feet from the entrance section, and 50 feet from the entrance section, and 75 feet from the entrance section, and the exit section. For with B column, since we know the entry width is 12 feet and the exit width is 6 feet, and we also know the length of this transition is 100 feet, so we can determine the width at this section. So the inlet is 12 feet and the exit is 6 feet, and we can determine the other widths at the other sections. So they are the 10.5 feet, 9 feet, and 7.5 feet. Let's add unit for each column. This is feet, 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 feet. And for the Z, since we know the channel bottom height at the inlet, the I is 884 feet, and we also know the length of the transition is 100 feet, so we can determine the bottom elevation at other sections. This section, and this section. And the value is for the inlet, Z is 8.84 feet. And for the XZ section, Z equals 0 feet. And for the section 25 feet from the entry section, so Z equals 6.63. For this section of Z equals 4.42, and for this section is Z equals 2.21 feet. And for the H column, the total energy head column, we can determine the energy head at the inlet. First, using this equation, HI equals ZI plus YI plus VI squared over the 2G. ZI is 8.84, and YI is the 5.88 we calculated before. Feet. So YI is 5.88 feet. And the VI equals 7.09 feet per second, so we can determine the total energy head at the inlet section. HI equals 15.50 feet. So this value is 15.50 feet. And then we can use this equation, H equals HI minus HL, the head loss for the other sections. Since we know the energy loss in the transition is 1.5 feet and is uniformly distributed throughout the transition length, and we also know the length of this transition is 100 feet, so we can determine the head loss in this section. And then we use HI minus the head loss, so we can get the energy head for the other sections. So they are the 50.13 feet, 14.5 feet, 14.38 feet, and 14 feet. For the specific energy column, since we know the E equals H minus Z, so for this column, the value equals this column minus this column. So the values for E for the other section is 0.66 feet, 8.5 feet, 10.33 feet, 12.17 feet, 14 feet. For the water depth column Y, we can use the equation that we know E equals Y plus Q squared divided over the 2G times A squared, and we know A equals B times Y. So now E equals Y plus q square over the 2g times b times y square. Since we know the q, the problem gave us the value 500 cubic feet per second, and we also know the b at each section. Yeah. And we also know the e at each section. So we can determine the y. So the values are 5.88 feet we calculated before, and for the exit it's 30.4 feet we also determined before. And for the other section the value is 7.94 and 9.80, 11.70. So now we have done this problem.